Hi everyone, my name is Darian and I'm a senior embedded software engineer in Espressif, and I'm part of the software platforms department, and I'm here to talk about FreeRTOS and ESP-IDF. So let's get started. So what I'm going to be covering today is some of the basics, since this talk is quite technical. I'll cover what multitasking is and what SMP or symmetric multiprocessing is. And afterwards, I'll cover a bit of history about ESP-IDF and how we came to use FreeRTOS. And then I'll cover some of the different implementations of FreeRTOS, such as vanilla, IDF SMP, and Amazon SMP. Furthermore, I'll cover some of the design differences between the implementations, and finally, the future plans of each implementation. So let's cover the basics. What is multitasking? So essentially, a CPU can only do one thing at a time. So if we want to create the illusion that the CPU is executing multiple things in parallel, the CPU can switch between tasks rapidly, and it will create the illusion that multiple tasks are running in parallel. So what is symmetric multiprocessing? The technical definition is a multi-core system where each CPU has access to the same memory bus. However, in the context of multitasking, symmetric multiprocessing just means that you have different tasks which can run on both CPUs, and if the CPUs switch between the tasks quick enough, then it will appear as if all four tasks are running in parallel on both CPUs. So that covers some of the basics. So let's talk about some history now. How did ESP-IDF come to use FreeRTOS? A long time ago, there was a chip called the ESP-8266, and this was paired with the ESP-8266 non-OS SDK. So the ESP-8266 was basically a single-core extensa architecture Wi-Fi SoC. And at the same time, there was a dual-core Wi-Fi SoC under development called the ESP32. So what were some of the pain points in using the non-OS SDK back then? So first, obviously, there was no operating system, so users couldn't schedule tasks or do any multitasking. It was also difficult to configure, as all of the configuration was provided in a header file with some macro defines. And finally, it was difficult to integrate other libraries, other third-party libraries into the SDK, as there was no clear project structure with the SDK. So this generated some requirements of the NICS SDK that would support the ESP32. First was there had to be an RTOS, and preferably this RTOS should support SMP, given that the ESP32 was going to be a dual-core SMP chip. Second, the SDK had to have a convenient way to configure. And the third requirement was that the SDK had to have a better build system structure, allowing users to easily integrate their third-party libraries or their own libraries into the SDK itself. So the result of that was the ESP-IDF. So the ESP-IDF came called a component-based SDK structure, where all of the different features were treated as different components in different directories. And within each directory, there will be a separate configuration file. And for the SDK, it used kconfig to support ease of user configuration. And finally, the operating system we chose was FreeRTOS, where we modified the single-core original version of FreeRTOS to support dual-core SMP. Some of you may be asking, why FreeRTOS and why modify it? So firstly, FreeRTOS is free and open software. It's quite popular and it's very lightweight. So given that it's popular, there's bound to be a lot of third-party support and third-party libraries that can easily integrate with FreeRTOS. And more importantly, FreeRTOS is a microkernel, meaning that it doesn't come with drivers or any network stack. So it fit quite well with the component structure of IDF, where you could treat FreeRTOS as a component, and then all of your other components, such as your network stack, your drivers, could simply call the FreeRTOS API as if it were a SDK component. So what are the different implementations of FreeRTOS in relation to ESP-IDF? There are three, which is vanilla FreeRTOS, IDF SMP FreeRTOS, and Amazon SMP FreeRTOS. Side note, these aren't any official names. They're just names given for the purpose of this presentation to differentiate between the implementations. So vanilla FreeRTOS is the traditional single-core FreeRTOS written by, I think, the real-time engineers, or Richard Barry, and is what you can find online. IDF SMP FreeRTOS is the dual-core SMP modified version that was written by us and integrated into IDF. And finally, there's Amazon SMP FreeRTOS, which is quite a recent addition, where Amazon themselves wrote an N-core SMP version of FreeRTOS, and N-core meaning that it can support more than 2 cores. So let's cover some of the highlights of each implementation and their advantages and disadvantages. So with vanilla FreeRTOS, as we've covered before, it's your standard single-core FreeRTOS. It's quite popular and it's got quite a long legacy. FreeRTOS basically provides all of the essential kernel features that you would want out of an RTOS. So synchronization primitives, task scheduling, interrupts, critical sections, etc. And it's also highly configurable. There's a list of FreeRTOS configs that you can provide to tweak the scheduler to your liking. So the advantages, extensive legacy, and it's quite stable given that it's pretty much used in a lot of places. And it's now actively maintained by Amazon. So there's a team of professionals working and actively maintaining and updating it. But what are some of the disadvantages? Well, it's single core, so it can't natively support some of our dual core chips like the ESP32 or the ESP32S3. And more importantly, it's not actually supported in ESP-IDF. So when you build for a single core ESP chip, it's not actually building vanilla FreeRTOS. So if it's not building vanilla FreeRTOS, what is it actually building? That's when we come to IDF SMP FreeRTOS. In order to support our dual core chips, such as the ESP32 and the ESP32S3, what happened was we took the original FreeRTOS and then modified it so that it could support dual core SMP. So the current version of ESP-IDF SMP FreeRTOS is based off the vanilla version 10.4.3 source code, where we took the 10.4.3 source code and then we applied the dual core SMP changes onto it. So, and even though it's dual core SMP, it can also run on single core targets. What happens is that you just set the number of cores configuration to 1. But what are the disadvantages? When you set the number of cores to 1, it's not actually running vanilla. So there are some subtle behavioral differences. And also, it doesn't support all of the vanilla FreeRTOS configurations. So I don't think we've ever tested IDF SMP with like preemption disabled, for example. So now we've come to Amazon SMP FreeRTOS. This was a recent addition. Amazon wrote a N-core capable SMP FreeRTOS version of FreeRTOS, and there's an experimental port of it within ESP-IDF where users can enable it using menu config. So what are the advantages? Well, obviously it supports N cores. So, in the future, if there's a possibility where there's an ESP chip with more than 2 cores, then Amazon SMP FreeRTOS is well positioned to immediately support that. And also, Amazon SMP FreeRTOS is actively maintained by Amazon. But what are the disadvantages? The port within ESP-IDF is still under development, so it's not in a completely stable state yet. So now that we've covered the 3 different implementations, what are some of the design differences of the 3 different implementations? So in terms of design differences, I'll cover their operating model, how tasks differ in each implementation, how the scheduling algorithm differs, the tick interrupts, how they differ, and finally critical sections. So let's talk about operating model. So within vanilla FreeRTOS, it's a single core operating system. So the user creates a bunch of tasks to parallelize their application, and some of those tasks will be blocked on events, and all of the tasks that aren't blocked are tasks that are ready. And of these ready state tasks, the CPU must pick one of them to execute at any one time. So every time the CPU picks a task, it will schedule task D, and the next time it schedules, it might pick a task E or something like that. So what about IDF SMP? It's a dual core SMP scheduler. So same concept with the block task and ready task, but from the ready task, there are now 2 CPUs, and each CPU must pick their own task to run. And a task cannot be run by 2 CPUs at any one time. So that's not allowed. And finally, with Amazon SMP FreeRTOS, this problem has now extended to n number of cores. So CPU 0, CPU 1, all the way up to CPU n-1. So let's overview some of the tasks. So a task in FreeRTOS is usually implemented as a function, and inside that function, there's some sort of infinite loop. Task can be within one of 4 states, which is running, ready, blocked, and suspended. When a task is created, it's usually in the ready state, meaning that it's ready to be run by a CPU. And if the CPU picks that task to execute, then the task turns from ready to running. However, sometimes the task might need to wait for a particular event. So in that case, when the task waits for something, i.e. calls a blocking API, then it gets put into the block state. And then after the task either receives the event it was waiting for, or it times out for the event. It times out waiting for that event, it will go back into the ready state. So the CPUs in vanilla, both vanilla and SMP, the CPUs always pick tasks from the ready state in order to run. And lastly, there's the suspended state, but basically the suspended state is similar to blocked, but tasks inside the suspended state aren't waiting for anything. They have to be explicitly suspended and explicitly resumed in order to be able to be scheduled. So here's an example of a FreeRTOS task. Tasks are implemented inside functions, and these functions are usually contain an infinite loop. Inside the infinite loop, the task will do some work. It might block on some event. So in this case, it's delaying for a particular amount of time. So after it delays, the task enters a block state. And then after executing some things, it might check for an exit condition. And if the task is ready to exit, then it'll jump out of the loop, in which case the task would delete itself. And one important note is that task functions should never return. So in this case, the task is deleting itself. And inside the deletion, it doesn't actually return from this function. So what are the differences in tasks between the various FreeRTOS implementations? Well, one of the first differences is the function call to create a task. In vanilla, you call xTaskCreate to create a task, where you call this function and then you provide the C function that implements the task. You give the task a name, its stack size, and you provide an argument for that task. And here you specify the task's priority. We'll get to how priority is used in scheduling later. And lastly, it has a return handle for the created task. However, with the SMP implementation, there's one more piece of information that must be provided about that task, and this is the core affinity. Because SMP systems have multiple cores, we have to specify which cores a task is allowed to run on. Thus, this is what the core affinity is. So in IDF SMP, because there's only 2 cores, the core affinity is specified as an index, meaning that as a core index, meaning that the number given represents the index number of the core. So IDF SMP, the possible values are 0 or 1, or the last one is the task no affinity. So 0 means that the task is only allowed to run on core 0, or in other words, pinned to core 0. And the value is 1, then it means that the task is pinned to core 1. And if the value is task no affinity, it means that the task can run on core 0 or core 1. However, with Amazon SMP FreeRTOS, things get a little bit more complicated because there are now n cores. Amazon SMP provides more flexibility as you can specify a combination of cores this task is allowed to run on. So the core affinity is provided as a bit mask. So for example, you might provide a value of, here's a binary number like 1101. This means that the task is allowed to run on core 0, not allowed to run on core 1, it's allowed to run on core 2, and it's allowed to run on core 3. So in order to specify that a task is allowed to run on all cores within Amazon SMP, you have to provide a bit mask of all ones. So here, the functions, corresponding functions in IDF SMP, you create a task using xTaskCreate pin to core, and here's the extra core index argument. With Amazon SMP, you use xTaskCreate affinity set, and here's where you provide the core affinity mask. Here are some of the task differences with the various implementations. Now let's talk about scheduling. So in vanilla FreeRTOS, the FreeRTOS scheduler can be said to have 3 main properties, which are fixed priority, round robin, and preemptive scheduling. So what does fixed priority mean? It means that, as we previously just mentioned, each task is created with a fixed priority, and in normal circumstances, the task priority remains static for the task's lifetime. So what does priority have to do with scheduling? When the scheduler goes and picks a task to run, it always picks the highest priority tasks that are in the ready state. So, but what if the current highest priority ready state has multiple tasks in it? then that's where we come to round robin. So if there are like 3 tasks that are in the ready state and are all of, for example, priority 10, then the scheduler will actually iterate over those 3 tasks in a round robin fashion. That means it'll go schedule task A and then B and then C and then back to A, B, and C, etc. And finally, preemptive scheduling. Let's say a higher priority task suddenly becomes ready. The scheduler will preemptive means that the scheduler will switch to that new higher priority task immediately, and it won't require the current previously running task to yield. So how does FreeRTOS actually implement the scheduling algorithm behind the scenes? So in vanilla FreeRTOS, there's a single CPU over here. And what FreeRTOS does is it actually maintains a bunch of task lists called the ready task list. And there's a separate list for each available priority. And inside each list contains all of the ready state tasks of that priority. So for example, if this is priority 10, then this list contains all of the priority 10 tasks that are in the ready state. So with fixed priority scheduling, what the scheduler does when it has to go find a task to run is that it searches from the top of the list, top of the highest priority list down to the lowest priority list. And it'll keep searching until it finds a ready state task to run. So in this case, let's say the CPU was scheduling a task. It'll check the highest priority list. There's nothing here, so it'll keep going down the list until it finds this priority where it finds task A, and then it runs task A. But what if there are multiple tasks within the same list? So let's say task A now blocks and gets moved over here to the block state. So the CPU has to schedule again, and it keeps looking down, and now it finds this priority. Let's say it's priority 9, and there are 3 tasks. Which one does it actually schedule? So this is when we get to round robin scheduling, which is covered here. So what FreeRTOS does when there are multiple tasks of the highest ready priority is that it will iterate between those tasks every time it's scheduled. So let's say this time the scheduler picked B. Next time when it comes to schedule, it'll pick C, and then next time it'll pick D, and then it'll loop back around to B, C, D, etc., etc. And how it actually implements this is internally within each list, there is a pointer to the last item returned from that list. So let's say the CPU picked B, then the pointer now points to B, saying that that was the last item returned. And next time it comes to schedule, it will just take the last pointer and then get the next item from that, and then the pointer moves up with it as well. So that's how round robin scheduling is done. And let's say for example that all of these tasks become blocked. There's a final idle task which never blocks. So this basically gives the CPU something to run if there are no other tasks available. And idle task is of priority 0, which is the lowest priority. So what about preemptive scheduling? So let's say using the previous example, what if the task A that was previously blocked suddenly unblocks? So as soon as task A unblocks, it is now the highest priority ready state task. So the CPU will immediately switch to running task A. So here's a timing diagram of the previous example we used. Let's say the CPU was running task A, and then task A from here blocks. And then after task A blocks, B, C, and D were of the same priority. So the scheduler basically round robins between B, C, and D until at some point task A unblocks. And because task A unblocks, it's the highest priority task, so the CPU continues running task B. And let's say enough time has passed until all of these tasks, all of the tasks A, B, C, and D have blocked or been deleted, then the final task that is still available is the idle task. So the CPU now runs the idle task. So what about scheduling in the SMP implementations? So there are 2 more things to consider when scheduling in SMP. First is, before a CPU scheduled a task, the CPU must first check whether the task has a compatible affinity, meaning that when a task was created, did the specified core affinity allow the task to be run on the current core? And the second is the task must not already be running by another core. So because of these considerations, this actually affects how fixed priority, round robin, and preemptive scheduling manifests within the SMP implementations. So for example, for fixed priority in SMP implementation, just because there are n cores does not mean that the n highest priority tasks are always run. For example, if the n highest priority tasks don't have a compatible affinity with one of the cores, then that core might be forced to go to an even lower priority to find a runnable task. And with round robin, same thing. Within a single task list, let's say there's A, B, and C. When a task is iterating over the list to find the next task to run, if that task does not have a compatible core affinity, it might have to skip over to the next one. So we won't get a perfect round robin within the same task list. And finally, preemptive scheduling. When a task unblocks, like in the previous example, so when a task unblocks, we have to actually decide which core would be preempted in order to run that higher priority task. So here's an example of fixed priority scheduling in SMP. So I'm using the IDF SMP here because there's 2 cores. So you notice that each of the tasks now have a core affinity on top of them. So for example, task A has no affinity, meaning that it can run on both CPU 0 and CPU 1. And task B, C, D have a core affinity of 0, which means that they can only run on CPU 0. Likewise, task F can only run on core 1. So let's say that CPU 0 and CPU 1 haven't scheduled anything yet. So let's say CPU 0 comes to schedule, it goes from the top of the list and then finds task A is the highest priority task. Task A isn't run by anyone else, and it also has compatible affinity. So CPU 0 runs task A. Now it comes to task CPU 1 to schedule. It goes down the list and finds task A is the highest ready priority task, and it also has compatible affinity. But CPU 1 can't run task A because it's already being run by CPU 0. So it has to go down the list and keep looking. It jumps down to the next priority. CPU 1 sees that there's task B, C, and D, but incompatible affinity, so it has to keep looking. So it goes down to one lower priority and then finds task E and F. Task E has a compatible affinity, so CPU 1 picks task E to run. And let's say CPU 0 comes back to schedule again, same flow, it goes down, finds task A, runs task A. But now when CPU 1 comes to schedule again, it goes down the similar flow, but because there are 2 tasks within the same priority, it will actually round robin and run task F on the next iteration. So the scheduling diagram will look something like this. For CPU 0, it would just be running task A all the way through. And in this case, with CPU 1, it will actually alternate between E and F. It will run a bit of E and then round robin to F, and then E and then F, etc., etc. In this example, CPU 1 was a bit lucky because within this same list, it could run both E and F. But what if there was a case where for CPU 1, it was running into a case where this task was pinned to core 0 and core 1 and core 0, where in a single list, there were some tasks which CPU 1 could not run. So it would mean that CPU 1, when round robining through the same list, would end up skipping over some tasks. So for example, it can't run this, so it'll skip over and run task 1. And then afterwards, it'll skip over 0 and then come back to task 1. So we can't use the vanilla FreeRTOS way of using the last item pointer of the list to get them to round robin within this given priority. So what do the SMP implementations actually do? The trick is to actually always search from the start of the list and also put the last run task to the end of the list. So let's say that this is all within the same priority. Let's say like priority 10, and priority 10 is also the highest priority. Let's say CPU 0 is running task A, CPU 1 is running task B, and the task affinities are listed below them. Let's say CPU 0 now has to do a reschedule. How does SMP handle the round robining in this case? So what happens is that because CPU 0 was previously running task A and CPU 0 is rescheduling, task A gets put to the back of the list. And then afterwards, CPU 0 must now start searching from the front of the list for the next task that it can run. So it sees task B, but it can't run task B because it's being run by CPU 1. So CPU 0 continues looking. It sees task C, can't run task C because it has an incompatible affinity. So it jumps to the next one and finally finds task D. CPU 0 can run task D, so what ends up happening is that CPU 0 schedules task D. So CPU 0 ends up scheduling task D, and the resultant list looks like this, where CPU 1 is still running task B, and the CPU 0 is now running task D. It's now CPU 1's turn to schedule. we do the same thing where we take CPU1's previously running task and we stick it to the back of the list, and then CPU1 starts searching from the front of the list for the next task it can run. It sees task C, so CPU1 starts running task C, which results in this. So CPU1 running task C and CPU0 running task D, like that. So now let's say it's back to CPU0's turn to reschedule. So CPU0 was previously running task D. We go here and stick it back to the end of the list. And then CPU0 starts searching from the front of the list for runnable tasks. It can't run task E, and then it jumps to task A. So CPU0 is now running task A. So CPU0 schedules task A. And the result of sticking the last run task to the back of the list and then searching from the front is that eventually all of the tasks will have a chance to run, as if a task was not run for a prolonged period of time, it will end up at the front of the list. So this doesn't produce a perfect round-robin scheduling, but it still gives that, it will avoid the scenario where a task is consistently being skipped over by CPUs when they're traversing a list. So now let's talk about preemptive scheduling in SMP. So let's say task A was previously blocked and is now unblocked and is also the highest priority task. So we have to pick which core to preempt. Does task A preempt CPU0 or does task A preempt CPU1? Well, the answer to that is it depends. So what does it depend on? In IDF SMP, when a task A unblocks, preemption only occurs if task A has a higher priority than one or more cores. And of those cores, task A has to have a compatible affinity with them. So for example, let's say this is priority 10 and this is priority 9. Task A is unblocked and task A is of priority 10. So task A has a higher priority than both CPU0 and CPU1. So that means that task A can technically preempt CPU0 and CPU1. But let's say now that task A is pinned to CPU0, then under no circumstances will task A ever preempt CPU1 because task A can't run on CPU1. But what if task A was not pinned to any of the cores and was also higher priority? Then in IDF SMP, there's a bias towards the current core. So what does this mean? It means that if task A was unblocked and it had no affinity, then whichever core caused this unblock will be responsible for being preempted. So for example, if core 0 was the one that caused task A to unblock, then task A would actually preempt core 0. And likewise, if core 1 was the one to unblock task A, then core 1 would be preempted. So this biasing is specific to IDF SMP. Let's take a look at Amazon SMP. So Amazon SMP has similar considerations where when task A unblocks, it has to have higher priority than one or more cores, and task A also has to have compatible affinity with those cores. And also, you can't have suspended the scheduler because if you suspend scheduling, then task switching basically stops. However, with regards to selecting which core to preempt, Amazon SMP will try to select the lowest priority core with compatible affinity to preempt. So what does that mean? So in a previous example, let's say task A was of priority equals to 10 and it had an affinity of, let's say it could run on core 0, core 1, and core 3, for example. So let's draw some cores here. Let's say 0, 1, 2, and 3. So because task A is can only run on 0, 1, and 3, it would never consider preempting task 2. And let's say it has a priority of 10, and let's say core 0 has a priority of 8 right now, core 1 is 7, and core 3 has 12. Well, priority 10 is less than core 12, so it won't preempt core 3. So what's left is core 0 and core 1. Since core 1 has the lowest priority, then core A ends up preempting core 1. So that's the preemption algorithm in Amazon SMP. So now let's talk about tick interrupt. So what is a tick interrupt? Within FreeRTOS and other operating systems, there is a periodic interrupt that occurs. So for example, interrupt that occurs every 1 millisecond. And that interrupt basically drives the entire operating system's timing. So every time the tick interrupt occurs, it increases something called a tick count. And the tick count is basically the current time of the operating system. And everything, all of the all timing related things within the FreeRTOS are measured in terms of ticks. So for example, if the tick interrupt happens every 1 millisecond, then the highest resolution of the length of delays is 1 millisecond. So when FreeRTOS runs a tick interrupt, the tick interrupt is responsible for incrementing the tick count. And because it increments the tick count, it will know what block tasks have now timed out. So it will unblock any tasks that have timed out. And then furthermore, it will also do something called time slicing, which is to check whether the CPU's current executing priority has other ready tasks of that same priority. And if so, force a reschedule. So what happens is that basically this is driving a periodicity of the round-robin scheduling. And finally, the tick interrupt runs a user-provided application tick hook. So about time slicing, let's take a look at an example. So for example, the tick interrupt happens at these intervals, so T1, T2, T3, T4, etc. And these are the current tasks available. So A is priority 2, B, C, D is priority 1. So let's say here's where time starts, and then task A is being run by the CPU, and then at some point task A blocks. So because task A is now blocked, the scheduler goes back to running task B and task C and task D. But because the tick interrupt forces a reschedule every tick, it causes the round robin schedule to happen every tick. So the result is that each of those tasks of the same priority get almost the same share of time, or the same amount of time slices. That's why it's called time slicing. And this time slicing repeats until task A gets unblocked. So task A gets unblocked and then let's say it blocks again, and then time slicing resumes. So time slicing basically is it's a mechanism to allow tasks to have almost an equal share of running time. That is to say, a task of equal priority have an equal share of running time, but it's not a completely equal distribution. So what about tick interrupts in IDF SMP? Now, this gets complicated by the existence of the extra core. So do we want both cores to increment the tick count or not? So in IDF SMP, both cores receive a periodic tick interrupt, but both of them, the responsibilities of each core are different when they come to execute the tick interrupt. So all of the timing related things, such as incrementing tick count and unblocking timed out tasks, that is delegated to core 0. So basically core 0 does almost all of the same things that the vanilla FreeRTOS tick interrupt does. But a small difference is that for time slicing, it only forces a reschedule for core 0. So when does core 1 do time slicing? Basically, when core 1's tick interrupt comes, then it will check for time slicing for its own core and also run the application tick hook. So for Amazon SMP, things are simplified even further. Basically, only core 1 has a tick interrupt, and core 1 will basically carry out all of the tick interrupt responsibilities. But for time slicing, it will actually check if each core's current priority has other tasks of the same, other ready state tasks of the same priority, and then force a reschedule on those cores if they can time slice, basically. And finally, let's talk about critical sections. So, quick overview. If two threads are concurrently accessing the same data, then there's a possibility that one thread corrupts the access of another thread. So the classic example is if two threads of execution try to increment a variable at the same time. Let's say the variable is 0, and then both try to increment it by 1. Then if both threads execute at the same time, then instead of the variable being incremented twice, the variable will end up being a value of 1 instead of 2. So a critical section is a section of code that cannot be executed by more than one thread. So basically what happens is that a critical section forces a piece of code to be serialized across when executed by multiple threads. So what are the possible concurrent threads of execution? There are software threads, which are basically other threads, other tasks, hardware threads, which is another CPU core running at the same time, and also ISRs. Basically, while you're incrementing the variable, an ISR could occur, in which case the ISR could also access the same variable, which could cause similar issues. So how are critical sections done in vanilla FreeRTOS? So in vanilla FreeRTOS, the only concurrent threads of execution are basically tasks and ISRs. So to guarantee that a section of code is only ever executed by one thread of execution, all we need to do is basically disable interrupt, because when we disable the interrupts, ISRs can't occur, and we can't switch to another task while interrupts are disabled either. So once we disable interrupts, we're guaranteed that only one thing can increment this variable at this time. However, with SMP, things get a little bit more complicated, because even if you disable interrupts, the other CPU still exists, and the other CPU is running something at the same time. So disabling interrupts is no longer sufficient to guarantee a critical section. So what we do in IDF SMP is that we use something called spin locks. Basically, before we enter a critical section, all threads of execution that want to access that shared piece of data have to take a lock. And basically, if a thread of execution has already taken a lock, other threads of execution, such as tasks, ISRs, or the other CPU, will basically spin in place until the current lock holder has released it. So in IDF, more specifically in IDF SMP, the locks are granular. So users can define their own data or their own object or structure, and then they can also define a lock to protect that data or object. And users can define their own users, or other IDF components will define their own locks, and they can control the amount of granularity. However, with Amazon SMP, the problems are similar, where the other CPU exists, and they also use spin locks, but the main difference is that critical sections now use a big kernel lock approach, meaning that all critical sections contest for the same lock. So there are some benefits to this, meaning the main one being that there's no possibility of deadlocking, and it also simplifies some of the concurrency issues within the operating system. However, a big downside to this is that all critical sections basically try to contest for the same lock. So if two threads of execution are accessing completely different pieces of data, and they both try to enter critical at the same time, they will still contest with each other. So this could lead to some basically lower performance in code. So now we've discussed all of the most of the major design differences. Let's now talk about the future plans of each implementation in ESP-IDF. So here's an overview of the different implementations, what the current status is, and main goals in the future are for each implementation. So vanilla FreeRTOS currently not supported in IDF, but we want to have some near vanilla support in ESP-IDF in the future. IDF SMP, it's based on the vanilla 10.4.3 code base, but we want to upgrade it to a newer LTS version before it becomes legacy. So why would IDF SMP become legacy? It's because we want to make Amazon SMP FreeRTOS the default OS in ESP-IDF some point in the future. So the current status of the Amazon SMP port in ESP-IDF is that it's quite experimental, and there's still some issues with it and some performance issues we need to solve. However, given enough time, we'll keep working on it, and then in the future, it will become the default FreeRTOS implementation within ESP-IDF. So let's go more in depth. Future plans for vanilla FreeRTOS. Currently, if you build FreeRTOS for a single core target, you're not actually running vanilla FreeRTOS. It's running IDF SMP with the number of cores set to 1. So the downside to that is that due to some of the design differences in IDF SMP, it's not immediately, we can't guarantee that application written for vanilla FreeRTOS would immediately work in IDF. So the reason for us wanting to provide a vanilla FreeRTOS or near vanilla FreeRTOS implementation within ESP-IDF is that users porting code for other single core FreeRTOS projects can immediately integrate them into ESP-IDF. So yep. So what does that involve? this will mean that we have to refactor our current IDF SMP FreeRTOS so that when config number cores is set to 1, it will basically restore vanilla FreeRTOS behavior or something very similar to it. And any places that deviate, we'll have to clearly document where the deviations are, where the deviations are, so that users who port code from other FreeRTOS projects will know what effects will have on their application. So what about future plans for IDF SMP? It's currently based on the vanilla FreeRTOS version 10.4.3 code base. So we basically took 10.4.3 vanilla FreeRTOS version 10.4.3, and then we added all of the IDF SMP modifications onto that code. So the goals for that is we want to update the base code to the next FreeRTOS LTS version, which is 10.x.y. We're not sure when that is, but we want to basically give it another LTS update before it turns legacy. And we also want to refactor the way the IDF SMP implementation is written so that it's easier to forward port to newer versions of FreeRTOS. Currently, what happens when we upgrade to a new port over the behavioral change. If we can isolate or find some convenient inject the changes, it will make behavior onto like vanilla code base. But some of you may be asking, why do we want to do this? It's because when IDF SMP finally becomes legacy, we still want to make it easy for like third-party users who want to continue using it to forward port it to newer versions of FreeRTOS. And finally, we have Amazon SMP. So currently, it's still an experimental port, and there are some known issues. So the main goal for this is to make it good enough to be the default FreeRTOS, which means resolving some of the known bugs and issues, improving performance, and also improving test coverage. And the final point is actually quite interesting. This is something that Amazon is currently working on. They have plans in the future to be able to merge the Amazon SMP FreeRTOS codebase with the vanilla one. So in the end, they will just have a single version of FreeRTOS, which can do single core and SMP. So I guess that covers everything. And I'm dropping some resources here for each of the FreeRTOS implementations. So please take a look if you're interested, and I'll take some questions. So thanks for listening.
Okay, perfect. So let's move on to the next Q&A session, and I will invite Darian, the speaker of this talk. Hello, Darian. Can you hear me?
All right. Hi, everyone. I can hear you. Can you hear me?
Perfect, perfect. So Darian, we have sorted a few questions for you. So I will just quickly start with the first one. And it's basically, what the heck is a semaphore?
So let's go through these quickly. A semaphore is a signaling mechanism between tasks. If you have a task A and a task B, and task B needs to wait for task A, then semaphore is one of the synchronization features you can use. The other options are mutexes, queues, and I think like event groups and task notifications are some other options you can use. But a semaphore is by far one of the most simple ones.
Okay.
All right. I hope that answers it. Next one.
Yeah. Don't hurry. Like we need to. Have someone to be able to follow us. So let's jump to the next one. And it's with the ESP-32, I have two cores which can assign to the task. So is it kind of a multitasking?
Well, yes, I guess like multitasking, this would be something known as like a true hardware thread. So in SMP FreeRTOS, you have a task, but the task can only be run on a particular CPU at any one point in time, but it's possible for the task to jump between the CPUs when it's switching. So yes, if you have two cores, it is multitasking.
Okay, perfect. Let's continue. The other question is there like any way for two CPUs to interact with each other, and how the single processing code can be built for a multiple core system?
So the CPUs can interact in many ways. So one way is at the FreeRTOS API level. So for example, if you have task A on core 0 and task B on core 1, it's perfectly valid for task A to communicate with task B using like a FreeRTOS queue or the previously mentioned semaphore. We've built IDF SMP FreeRTOS so that like the API works across cores. And how to build like how to build like single processing code for multiple core systems. You just write a regular FreeRTOS task. It should work on multiple cores. So the amount of changes you need should be minimal.
Okay, perfect. Thanks a lot for a nice answer. The next question is shorter. So Xtask, right, is also part of ESP-IDF. Is this correct?
Yes, it is. It will just basically create a task that is not pinned to any core, meaning that it can run on any core.
Okay, perfect. The other one, how about the wedge-dog bug? I actually stopped working on the ESP-32 after that project. It's not nice to read that. So
this is a question we get very commonly, and the most common reason for the task watchdog triggering is that the idle task isn't allowed to run within a certain period of time. So the task watchdog is there to guarantee that at some point in time, the idle task is allowed to run. So why do we need the idle task to run? It's to guarantee that your CPU isn't being oversaturated with tasks. So the solution to that is find out what task is preventing the idle task from running and then try to make that task block for some event. So either a delay or block on some queue or semaphore or something.
Okay, so I hope it's now clear to the users, and maybe you will just return back to the project.
Yeah.
And the next question, is it possible to change the frequency of time slicing? For example, every ticks?
Yep, there's a config option called config FreeRTOS HC for like hertz, and you can adjust your time slicing frequency there.
Okay, perfect. And I think we are just like running out of the time, so I think I will have the last question for you, Darian.
Okay.
Let's highlight it. Why do you want to turn IDF SMP to the legacy if it works well with 2-cores ESP-32 SoCs? I mean, Amazon will implement N-core, but IDF SMP can be specialized for 2 cores.
So I think in the future, we want the flexibility to implement in N-cores. And by turning it legacy, it doesn't mean that you can't run IDF SMP FreeRTOS. I think at the end of the talk, I mentioned that we want to make it possible for third-party users to continue forward-pointing IDF SMP to future FreeRTOS releases if they want to, because we understand that like IDF SMP has been around and it's stable, so users want to stay with that. So I think even though Amazon SMP will become the default FreeRTOS in the future, we'll still have some ways for either third-party users to have a way to run IDF SMP, so it won't be completely like unusable.
Okay. So as you promised, you are answering fast, so we can extend a bit. And this is the last question. And it's, will ESP-IDF actually work at super low tick rates? Like one...
Technically, yes, but it's a trade-off between overhead and precision. So your tick rate defines the precision of your delay. So if you have a tick rate of 10 megahertz, then the highest precision you can get with your delay is 10 milliseconds. So the higher tick rate, the more frequently your CPU has to be interrupted to process those tick interrupts. The lower your tick rate is, the less overhead, but the less precision you get with your delays.
Okay, perfect. So I think that's it. Darian, thank you a lot for joining. It was nice to have you here.
All right.
For the audience,
thank you.
If you still have some questions, don't hesitate to ask in the YouTube chat. I think Darian will be available for some time, so he can answer.
Yeah, I'll stick around to answer more questions. All right, thanks for having me.
Thank you, Darian. See you. Bye-bye.
Bye.
So guys, we have finished the first block of the talks. Now we will follow up with the 15 minutes breaks. And during that break, it's going to be a static picture, but there's also some like videos from the Espressif based makers. So you can watch them and maybe just check their projects, what they are working on. And see you after 15 minutes break in the second block of the talks. Bye-bye.